Those were some of the changes in temperature that have been observed in the forecast for changes in temperature into the future. There's also changes in precipitation that have occurred and are expected to occur into the future. Here are the observed changes in precipitation in the US. This is a comparison of temperatures in different regions from the latest decade from 2001 to 2011 versus essentially an average from the first half of the 20th century. Here's the US average, and you can see on average increases in precipitation, but not all places have actually seen changes in precipitation. The scale here, greater than 15% change increase is all green, less than 15% increase, less than a 15% increase here. So essentially 15, 20, 25% decline in precipitation. As you can see, there's a dividing line into different regions, but those places that are relatively wet and northern, we're seeing increases in precipitation, and that's something that we expect. We're going to get a lot more evaporation coming off of the oceans and gulfs, and that pushes more moisture onto the continent. Wetter places are essentially getting wetter. Drier places, for all intents and purposes, are going to get drier. And we can see that there are regions that are relatively dry that are also getting drier. They're seeing decreases in precipitation. So it's true, we're seeing increases in precipitation throughout most of the continental US, and that's, for example, what's expected just based on having warmer temperatures, more evaporation, and knowing that a large proportion of the precipitation directly comes from the oceans. Those oceans are getting warmer, and they should be evaporating more water and delivering more water onto land. The changes in precipitation are on average, and they're averaged generally on an annual basis, sometimes a decadal basis. But we also see that extreme events are becoming more extreme, they're becoming more frequent. Here's one of the examples that they use. This is the summer of 2011 in Texas, and they had record heat and drought. Extreme events come often. There are droughts and there are heat waves, and heat waves and drought are part of the natural variability of ecosystems. What this graph shows is essentially that the types of record heat that we're seeing and the record droughts that are occurring, we haven't observed in the past 100 years. These are data from 1919 through 2011. And this is the total rainfall in inches, June, July, and August, so 3 different months. It goes from 0 inches up to 14 inches for that 3-month period. This is June through August average temperature, so it's the average temperature during that 3-month period. You can see that there's a lot of variability, and generally when it's hot, it's also dry. So hotter temperatures, less rainfall, more rainfall, cooler. And those two things tend to go together. There's variability in that, but if it's cloudy and rainy, you tend not to get the high temperatures, and the feedbacks that occur from it being dry, as far as sensible heat versus latent heat flux, tend to exacerbate situations or positive feedback. Drier temperatures are hotter. What happened in 2011 had never been seen before. 1934 was the middle of the Great Drought of the 30s, and that was probably some of the most extreme droughts that we had witnessed. This general relationship is here, and you can see some of the data from recent years. Here's 2010, for example, but 2011 was off the charts. It was the driest time and the hottest time that's ever been observed. And this is something that we kind of expect to see, that the changes in temperature that are occurring, there's going to be positive feedbacks, and we think that the extremes should be getting more extreme. And we saw that in 2011. It was a year like anything else that had ever been observed in Texas. With greater precipitation comes a trend for increases in heavy precipitation. So extreme events, large events. So here they take a look at 2-day precipitation that is exceeded on average only once in a 5-year period. So it's a once in a 5-year event. So how often are we getting these once in a 5-year events? And over time, we're seeing an increase in these large storms. So we're getting heavy downpours, and those heavy downpours are actually a lot more frequent today than they were before. So on the water side, we talked about how there's going to be greater evaporation. We should also be seeing changes in sea level. So there should be thermal expansion occurring in the ocean that would increase sea levels, as well as greater melting of the ice caps. And it's the terrestrial ice caps that are important, not the sea ice for changing sea level. Here are some of the patterns for the sea level rise, past, present, and future. These are proxy records that go back before records were taken. Here's some tide gauge data, so this is actual data. And then we're starting to use satellite data in more modern periods to get better global estimates of what sea level is. And then they're going to show future scenarios. This is year, starts at 1800 and goes to 2100. And this is global sea level rise. Again, it's in feet because we're here in the US. We're out of the metric system. When we take a look at the patterns, here's the proxy records that show, to be honest, there was somewhere on the order of 2,000 years of pretty steady sea level. And starting somewhere around the Industrial Revolution, we started to see increases in sea level. And these are from tide gauge data. Arbitrarily, the year 2000 is set at 0. And essentially to this point in time, we've seen on the order of 8 inches rise in sea level. The scenarios into the future call for somewhere on the order of 1 to potentially as high as 6.5 feet of increase in sea level. Now that's due to differences in emissions and what's going to happen essentially with thermal expansion and changes in ice over Greenland and Antarctica. But when you take a look at the data, whether it's this general pattern or when we've taken a look at satellite data, we're seeing an increasing rate in sea level rise also. So sea level is continuing to rise, and it's increasing, and the rate at which it increases is increasing too. So we have a wide range of potential scenarios and outcomes for sea level rise, but we've already seen 8 inches increase as far as we can tell, and we're likely to see feet of increase more. Some of the consequences of this are probably best shown for the southern part of the US. In white are areas that are 4 feet above sea level. And blue are those places that are 4 feet below sea level. 4 feet is a reasonable estimate for how much increase in sea level we're going to see by the year 2100. And essentially this is Interstate 10. And almost all of the area below Interstate 10 is going to become flooded. And that's on average, so we're not talking about storm events and surges, we're just talking about average sea level. So almost this in New Orleans we already know is below sea level, but a whole large contiguous area is likely to go under the ocean. And almost everything south of I-10 is going to become submerged. The National Climate Assessment also discusses some of the changes in ocean acidity that occurs as a consequence of increases in temperature. And this is a pretty good synthesis. We've already talked about some of the basics of why as oceans absorb CO2, they become more acidic. So we get carbonic acid and carbonates, bicarbonate that forms that releases acidity. Here they're going to show atmospheric CO2 concentrations, measurements of seawater CO2 concentrations, and seawater pH. Since 1960, here are the changes in CO2 concentrations that we've seen. So they've gone up. And this is the changes in CO2 concentrations that actually have been observed in seawater. So we're seeing increases in the partial pressure of CO2 in water. So the CO2 concentration in water has been going up. As a consequence, seawater pH has been going down. So we're looking at 8.13, 8.08, and those don't seem like big changes in pH, but remember pH is a log scale, and I think the estimate was somewhere on the order of 30% more acidity has already been observed. It's not hard to take this line and continue to bring it down to where we're down to a pH of somewhere on the order of 8. What are the consequences of acidified ocean water? We talked about how calcium carbonate becomes a lot more soluble as it becomes more acidic. And here's a demonstration of what happens to a shell primarily made of calcium carbonate when it's put into acidified ocean water. Now, if I remember correctly, the pH that they used here was essentially the pH that's forecast to be slightly into the future. And you take that shell and put it in, and within 30 days, it's dissolved almost to nothing. And 45 days isn't even recognizable. If you're an organism that requires a calcium carbonate shell, and you're trying to grow in acidified ocean water, you're not going to do well. And we're going to see huge changes in the structure of the food webs within the oceans simply because of changes in pH.